Hey everyone, this is Illia joining from Bay Area, Palo Alto. It's amazing to be in the office of Aptos. So we have Avery and Sasha from Aptos. Guys, introduce yourself and let's dig in.
Great, I'll just keep it short. I'm Avery, co-founder and CTO here at Aptos.
Sasha, head of research at Aptos Labs.
Awesome, so let's dive in. So let's maybe explain what you're trying to achieve with Aptos and then go from there and start decomposing the system.
Sure, so just a little bit of history about Aptos. 2018, Meta started kind of launching an initiative called Libra and then Diem over time. I was very fortunate to work with folks like Sasha and a bunch of other people on our team on this project from almost day one. And the idea was, how do we kind of support the use case of billions of people at Meta and beyond that, be able to leverage decentralized technology to do things like remittance and payments and support like the largest use cases in the world. And so from that kind of point on, we thought about, from a first principle standpoint, what do we want out of a decentralized infrastructure? And that started off with the idea of a blockchain, like thinking about the way that we scaled systems at Meta before in the past, scaling to massive amounts of transaction throughput, maintaining great latency, and then from a language perspective, how do you kind of think about smart contract languages from the beginning again? If you think about the general purpose languages, they're built to support very different things: high performance, fast iteration, fast development times, fix bugs in prod, roll forward, that kind of thing. Whereas smart contract development, harder to fix bugs that are live already in the network. Also dealing with the idea that these bugs may cause massive asset loss, of course, is a huge problem. And so with that, we kind of have the idea of a move language coming forward, the idea of the Diem blockchain going forward, and then building these in tandem, the same way you kind of think about hardware, software, co-design, being able to think about the developer platform and kind of the infrastructure behind it, working in tandem towards this ultimate goal of mass scale adoption.
All right. So for later ones, I usually like to go from bottom to the top. So consensus, kind of the design of the state and transaction processing,
Yep.
and then VM, and then kind of polish on VM around like gas transactions, etc.
Sure, we can do that.
Yeah.
I thought maybe it'll also be useful to think about like the way our architecture is set up.
Sure,
That might be an easy way to start off with. So the first thing we have in the way we think about transaction processing is a data dissemination phase. And so you have clients that are going to be basically pushing transactions into validators. And so we have the notion of a validator set. There are many different validators here that all have fully connected. One more here. And clients can kind of send these transactions to any one of these validators.
Mm-hmm.
And in order to make sure we leverage effective use of this bandwidth, we leverage something called like a narwhal, which Sasha actually worked on, that technique, and it's also called Quorum store in our current model. And so the idea is that by having each of these validators kind of producing their own blocks and then being able to pass those blocks off to each other, we can leverage the full bandwidth of the validator set itself. And so if you think about like traditionally in many older systems, you have this idea of a leader-based protocol. A leader kind of pushes transactions to other validators in the network. You have to deal with kind of either a limitation of bandwidth and or a latency delay. And so, for instance, if each of these nodes has like n bandwidth, and I can, have a leader that's pushing out to these other two nodes, I have to divide this bandwidth out going into two, and I can push these transactions at a rate of n over 2. And this then slows the rate at which I can kind of get my consensus completed over time. And so instead, what you have here is everyone is going to be broadcasting these transactions that they receive in blocks to each other, kind of all-to-all communication. But they're leveraging that n over 2 bandwidth, and now you're also receiving n over 2 bandwidth, which means you kind of get a full utilization of your network pipe, which is great. The next phase is where we call consensus. And so for consensus, we've actually iterated a lot over this design over time. We started off with ideas of hot stuff. This is kind of my first project I worked on when I was at Meta. And I think we quickly realized there were things that were missing, like there was no pacemaker. There was the idea of you just having exponential back off until you kind of achieve this partial synchrony model, but that in practice, that works really, really poorly. And so we started to make changes to it, like adding things like leader reputation, where you could kind of support the idea of how the leaders done in the past. Have they voted? Have they proposed correctly, successfully in the past? And then also things around an active pacemaker, where we kind of proactively, if you see like the leaders miss around, you can kind of start broadcasting to each other and trying to figure out who the next leader ought to be and advance that cycle forward faster. That kind of led into a new line of work, which Narwhal and Tusk is one thing, and then Bullshark protocol, which is the DAG-based protocol, and then finally onto Shoal. But the idea here is that we have our consensus protocol here that doesn't agree, it doesn't pass off transactions as a part of that protocol. That propagation is happening in the first stage of data dissemination. And this is where a lot of the bandwidth goes, because if you think about it, again, the system, every validator needs to receive every transaction eventually and every executed output. And this is the bulk of the traffic, and that's where we maximize our throughput in the system. Then we have our consensus protocol. And as part of consensus, we also kind of have this interesting Oracle services built into it. And so we have timestamps that are built in. And we also have on-chain randomness, which is really interesting, which I probably won't dig into too much because it's a little bit deep. But the timestamp process is as a part of the consensus protocol, you only vote when certain times are passed. Times are part of the voting protocol itself. And that means that every single block has this timestamp associated with it. And typically in Aptos, you see something like 200 to 250 millisecond blocks. And every time you have this very accurate clock that kind of goes forward with that process. After this, we have parallel execution. Sorry about that, bad handwriting. And so at this point in the process, we have agreed on a set of transactions that will be kind of up for execution. And so you kind of imagine these set of blocks, like block 0, and then block 1, block 2, all full of transactions. So TX0, TX1, TX2, TX3, so on and so forth. And this is where I think a lot of the magic happens that I'll let kind of Sasha run into. But we leverage BlockSTM as a technique for dynamic kind of parallelism. We can kind of evaluate all the transactions. We currently evaluate block by block, but you can imagine looking at a window of blocks. And the idea here is that you have this set of transactions you're going to execute, and we want to make sure we fill up all the resources in the computer. So all the CPU cores, all the memory we have, all the SSDs, so on and so forth. We want to leverage all those resources to maximize and execute as much as we can in parallel. The next phase is going to be on the batch storage. And so once you kind of have done all this execution, you need to write to in our case, SSD. In many cases, I think that's the case. And so what happens is, we try to bulk up our writes into larger operations. This allows us to maximize the throughput and reduce the number of seeks that are necessary. We also start to explore how do we take our RocksDB instances and scale them out to multiple instances. So you have a couple of these in the back end. And this allows you actually get much higher throughput. We call this kind of storage sharding. It is an internal sharding technique. It does not require anything user visible. Just gives us a lot more throughput on kind of a critical path of our system. And the final phase is kind of the proof generation. So at this point, we kind of generate the proof on the state root hash, and then we broadcast this to other validators in the network. And so at this point, once you have 2L+1 stake in the system that has a proof on it, you kind of know that this is the state that's agreed upon. You can use this for state synchronization. You can use this for light client proofs, any kind of things like that. So I think what's also important to think about this design is that each of these phases can be executed all in parallel. The dissemination is consistently going on, consensus is consistently going on, execution, storage, and proof generation all happen at the same time. And so this means we can kind of leverage all the machine resources pretty efficiently. And also we can, if you think about it, we can expand this software stack to work on a set of machines over time as well, because every phase is kind of inherently pretty parallel. So any questions, thoughts?
Yeah, a lot. So.
Yeah, let's start digging through this. Yes.
Yeah, let's start digging in. Okay, so data dissemination, right? So you have a bunch of validators. They're interconnected.
Yes.
So let's say I'm validator 1. I received a transaction. What am I I'm just sending it out to everybody else. What are the guarantees that I'm looking for?
Yep. So the first thing you're going to do is you're going to basically broadcast to other validators in the network. Mm-hmm. And first you wait a period of time, a small period of time. You batch it up, and the batching is meant to be more like a efficiency win, right? We can process transaction by transaction, but that's not very efficient for the system, right? So by batching, you have a signature now on that batch. Mm-hmm. We call this the proof availability. I'll write this down. Proof availability. And this kind of, when you sign this, you're saying, I'm going to store this data. I'm not going to forget about it, right? And that way, when I start going to consensus, I'm sending this proof, and I'm agreeing on these proofs. And the important thing about these proofs means that I don't actually even need the transactions to vote on the transactions I'm agreeing on. I can fetch those just prior to the parallel execution phase.
Okay, so yeah, so pretty much there's like small batches of transactions that, as you said, you wait for like smaller amount of time, like
Very short period of time, yeah, kind of customizable depending on each validator.
yeah. Then you have a signature. I send it to everybody else. Do they like if they have the same transaction and they shared it? What is a
So you're actually like, what happens with duplicate transactions?
duplicate transactions as well as like do they propagate it? I mean, you're saying everybody's interconnected. What if
Yes.
like some links are severed?
Yeah. So if some links are severed, like as long as when a validator broadcasts this information to others, they're getting the proof availability. They're getting 2f+1 stake signatures.
So they're collecting like for any transactions, they pretty much
For a batch. For a batch.
For a batch.
For a batch of transactions, you collect this proof availability on it.
Okay, so I create my batch, I send it to everybody else,
Yes.
and everybody else then signs as well this batch and sends it to everybody else.
No, they sign it, and since you're broadcasting it, since the creator of the batch is responsible for making sure everyone gets it,
Okay.
they don't need to broadcast to anybody else necessarily. What happens is that this validator is kind of responsible for making sure it's disseminated.
Yeah.
If for whatever reason they don't receive it before execution, they'll have to fetch it, and they can fetch it when you have this proof of availability. You know exactly who has it. You know who you can go get it from.
But how does this get aggregated? Like by whoever disseminated it?
Yes.
Okay, so you send it and they reply with their signatures that they
Yes.
received it. Okay,
Yes,
so you
yes.
just you collect receipts. Okay.
Yes, and then
So
you broadcast that information. And that information now is that information, which is the proof of availability, is used in the consensus protocol.
Okay. So now pretty much when you move into consensus protocol, you have like batch validator 1, for example, batch validator 2 with a bunch of signatures, right?
Yeah, and they're aggregated, but yes.
Yeah. Well, yeah, aggregate signature.
Yeah.
Is it like BLS?
Yes.
Okay. All right. So you have these batches.
Mm-hmm.
Okay. And then so now consensus is what actually orders them.
Yes, and I think it's less of an ordering, which is important here. What is you're kind of agreeing on that set of transactions, and the reason why I call that out specifically is that when it comes time to we've agreed on these blocks basically, and we've agreed that these will be sent to execution. The nice thing is that kind of at runtime here, as long as the validators agree on it, they can do all kinds of interesting transformations on that data.
Sure.
They can reorder it to maybe thwart some MEV type attacks if you want to. You can also try to extend that window if you want to achieve more concurrency in the way that you execute those transactions. You can even optimize if you want to do it around gas as well. Like if you want to think about the way that gas markets work and prioritizing certain transactions, we can also add the optimization there. So it's kind of like a late stage runtime optimization problem around parallelism, gas fees, as well as any other kind of objectives your optimization function is targeted for.
Okay, but I mean, you want everybody to execute in the same order, right?
Yeah,
So
they have
ordering.
to have the same process for.
Okay. So you mean like your protocol can
Exactly.
decide how to execute them?
Exactly. So over time, the protocol can evolve depending on the kind of the needs and desires of the network.
Okay.
Which is really nice. Yeah.
Okay. So how does this batches transform into this
Right.
block?
So I have these. Essentially, we have these proof availability.
Yeah.
Kind of things. So you have this. Maybe like a hash or something like that, and you have this, the signatures, right? And you kind of have a bunch of these.
Yeah.
And these are then, in consensus, someone's proposing that this is the thing we agree on. And once you get the agreement on this, at this point in time, you should have probably received this batch if the validator is broadcasting this stuff to everybody. And if not, then I said before you execute, you'll go and fetch that data. And so now you end up with the block, which has all these transactions kind of matching to each of these. This is like the batch of actual transactions now, TX0, TX1, all that stuff. And so you kind of make sure all that information is present in the execution there before you execute.
Okay. And so this is still a
This is
leader-based consensus. And so somebody rotate between validators who is actually proposing a block.
Yes.
They look at whatever they received, the proof of availability, order them, and kind of then the leader execute, like, is this happens on the leader pretty
So
much?
this is all happening. Everyone's happening. So yeah, let me show you. Let me draw the exact so data dissemination. There's kind of a, everyone's all validators are talking to each other essentially here. In consensus, they're all talking to each other as well. But here you're talking about like the proof availabilities essentially. And then here, this is no networking, unless there's fetching. If you're missing blocks, batches of transactions, you'll fetch them.
So here, leader says, okay, these are the batches that then block, and then sends it to everybody else.
These are they send the only proof availabilities.
Availabilities, and now everybody can execute in parallel.
Exactly.
Yeah.
And then this is going to happen locally on each machine, and this is going to be generated locally, and then broadcast to everyone so they can agree on the 2+1. 2+1
signatures on this.
stake.
Yeah. So in this case, the only thing your leader needs is pretty much say, these are the proof availabilities included, here's my signature, everybody executes it.
Yeah.
And
there's a lot of magic that happens in the consensus. I mean, we're skipping over some magic in the consensus.
Yeah, protocol. I would like to zoom in into that more, but we can do it. Okay, then everybody executes it in parallel, and parallel executes it.
Yes.
And then, storage, proof generation.
Yeah.
And then they sent out,
this is the certificate, the state roots. Yeah,
state roots signed by the individual validator.
Yeah, and then you get the 2+1 stake on this, 2+1 SIGs on this. Yeah.
And so everybody just broadcasts to everybody else hey,
it's a very small amount of data. It's just a quick broadcast. And that you can use again for like client proofs and all the fun stuff.
So here you have like very low kind of latency around creating the batches. How frequently does the leader create kind of a block?
This is pretty much just consistently ongoing.
But like what's it needs
to
accumulate some number,
like I said, what we have is like the block time is around 200 to 250 milliseconds today.
Got it.
Yeah. So that's every time there's a block created. That includes kind of all of the consensus. Now, of course, this is the happy path. But in most cases, I think in many blockchains we see the happy path.
And then, so this can take arbitrary, some amount of time.
This depends on the execution,
On execution. Yes. Do you have a limit on, how do you limit the...
Yeah, so each block has a kind of a gas limit individually. And there are a couple of different limits here with respect to I/O, to CPU, compute gas and storage as well. And the idea is you don't want to have any blocking any others too long. But at the same time, like I said, the interesting thing is you think about looking at a window that's beyond a block. You can start to think about maybe it doesn't matter as much to have those limits. It's just for now we start with the limits and see how it goes.
Yeah. Then batch storage generation. So this is in a way. Validators are continuously processing, right? They actually don't need this per se.
They don't need that. They don't need that technically. So this is a stage that we could actually remove in theory, but we like this just because it allows us to actually support the state sync.
Well, for clients and state sync,
those are nice things. And we don't do this. This is actually done on a block basis, and you could change you can customize how frequently you want to do the proof generation, and then think about for a client, it means you have to do some extra execution, which is kind of annoying. Or find other longer proofs to satisfy the client demands.
Yeah. Okay, makes sense. Would love to zoom into consensus, into the magic, but
we can zoom into consensus as well.
Yeah, and then we can dive in more into execution and move as well, and then
sure. Let's do that. Actually, maybe for consensus, Sasha, do you want to?
Yeah, sure.
Yeah, I'll let you get into that. He's been working on a lot of our consensus protocols for a long time. You can probably talk about where we're at and where we're going to. This is a tough eraser. They wrote too much here.
I think the black color was the black color.
Yeah.
That's a workout you get.
It's the only workout we're getting these days, man. All right. Go for it, Sasha.
All right. So consensus.
Yeah.
Let's talk about the new consensus.
Let's do it.
Yeah, so we're going to switch into a DAG-based consensus. Basically, like Avery said, the bottleneck in the leader-based consensus is the leader. Like if you think about it, you have one leader that needs to disseminate the data to all the validators, then the entire performance of the consensus is determined by the ability of the leader to push data. Right? So wanna eliminate that. And this, what we talked about data dissemination, then this is basically what we're doing. We have, instead of the data, everybody are doing it in parallel. This is validator. One of the validators, validator 1, is going to transmit the data to everybody, collect the signatures back, and then here he has proof of availability, and then this is going to go into consensus. I just want to summarize what Avery said, and this happening in parallel. All validators doing
all
the same.
validators doing this.
Yeah. So let me erase this thing. Okay, but we have like so now we have, like, if you remember data dissemination, then consensus. Consensus is a black box. We can use any consensus with this metadata, and we can scale any consensus. Now the question becomes like, how far we can scale it and what's the latency. So currently we have this data dissemination. It's 1.5 round trips, which we need to add to the consensus, whatever consensus we're using, right?
Yeah.
So what we want to do, we want to merge them. And also, even if the metadata now is small, the leader can still be a bottleneck. If there are a lot of proofs, still we can see that the leader is a bottleneck. So we're moving to a DAG-based consensus. Basically, what it means is that there is no leader. It's leaderless. So what we're going to do is the following. There is like 2 separated processes. First, we want to build a DAG. After we have a DAG, we will order the DAG. So this is how the DAG is going to look like. I'm going to use 4 validators because that's the minimum we need in order to do 3F+1. So these are the validators: validator 1, validator 2, validator 3, validator 4. And the DAG is going to be constructed in a round-based manner. These are going to be the rounds. So in every round, I'm going to, let's say this is the beginning, Genesis. Then I'm going to produce a new round, I can contribute a new node. And this node needs to link to n-f, which is 2f+1, in our case 3, nodes from the previous round. This is how we collectively advance the DAG. We're building the DAG, that's all we're doing. Like, forget about consensus for a second, we're building the DAG. Each of these nodes is going to contain this proof of availability that we said before, I'm proposing, and also I'm going to link. So it doesn't have to be the same links, right? It can be slightly different, and this is how the DAG is gonna grow. And I can move on to the next round once I receive 2F+1 nodes in this round, because I can already link to them, and I can broadcast my next node. And this is a local view of one of the validators, because the processes continue completely asynchronously, no timeouts, nothing. You just wait for this 2F+1 to link to, you propose a new node, you move forward. So each validator might see slightly different view of the DAG, but the important property here is that because we're not just sending the nodes, we're actually using something that's called consistent broadcast. It's like a weaker form of reliable broadcast, which guarantees that if we both see this node, it's going to be the same node. Like, there is no equivocation. This validator, even though it might be Byzantine and it's trying to lie, it cannot. Because the way it's going to work is that I'm going to send you the node. Like, each of these nodes is actually hide 1.5 round trips. Each of these round. I'm going to send you a node to everybody. They're going to send it back to me. I'm going to aggregate the signatures. And now I have the certificate, and then I'm gonna send you this node again with the certificate, and then you're gonna add it to the DAG. So I cannot equivocate, and I cannot produce certificate to two different nodes in the same round. So the property here is that we have 2 validators. They might see slightly different view of the DAG, but whatever they see is the same. And then also, and it means that if we both see this node, it's gonna be the same, and the entire causal history is gonna be the same, because the links are the same, and like we can go back and everything is the same. So this is what we are doing. We keep doing it. There's no timeout. We just keep building it. And now the question is, okay, so we build it. That's nice. And this is completely symmetric protocol. There's no leader. Everything perfectly load balanced. That's a very nice property. Now the real magic here is that why I think people are like these protocols now is that once I do that, I don't do anything else in order to have the consensus.
Yeah, now you know the consensus is 2/3 and 2/3.
No, that's actually challenging. You need to go and order all of this, right? Because we might see slightly different DAGs, but how can we order it? I mean, I I can do 1, 2, 3, 4, 5, 6, 7. You may decide it's a different order, right? So there is, I don't know if you want to go into the specific details of how load.
Yeah.
You want to go?
Yeah, let's go, yeah.
Yeah, let's go? Okay, cool, okay, let's go, yeah. So, good. So we're going to I'm going to explain bull shark now, and then shoal is actually an improvement on top of it, but let's start with bull shark. So we have these rounds, right? So this round is going to be an encore round, and this is going to be a vote round, and so on and so forth. This is going to be an encore round, and this is going to be a vote round. So by encore, before that, I want to say that we're going to look. Each validator is going to look on this DAG and interpret. What's the word there? And look at it as a consensus protocol. This is going to be the proposals, and the links are going to be the votes. Mentally, this is how the validator is going to see it. So before running the protocol, there is some a priori agreement on the encores. There is some mapping. You can think of a round robin or whatever, and we can later expand it to whatever we said. We have this leader reputation to use the history in order to choose the future encores based on the strong validators. But okay, let's say there is some mapping. So let's say that he is going to be an encore. This validator is going to be an encore. And in the future, we have other encores. So we all agree on this. Who is going to be the encores? This is easy. We just put some function, right? Deterministic function. Now the goal is to go and we want to order the entire thing, but we're going to go it in steps. First, we're going to order the encores. We're going to basically decide which encore I want to order and which encore I can skip. And even though we see slightly different views of the DAG, we want to come up to the same conclusion. This is for safety, right? So, and this is the first step, and the next step is trivial, because then what we're going to do, we're going to go order by encore by encore what we ordered, and we're just going to order the causal history by some deterministic rule. Again, remember we said that all the causal histories are the same. If you apply the same deterministic rule, you're going to end up with the same total order. So really the challenge is to decide which encores to order and which to skip. We even know which encores are the candidates. We just need to decide which we're not skipping. So here is the logic. This is pretty simple. So we're going to go, let's say we have a DAG, okay? Now we want to order it. And I have some local view of the DAG. So I'm going to see, and okay, how we're going to draw it. So the example will be nice. Yeah, okay. I'm going to go encore by encore and do the following. I will try first to directly commit this encore. The commit rule is that if I have f+1 votes for the encore, a vote is just a link from the next round. So in this case, we have 1, 2, 3, even 4, right? We have 4 votes, we can order this encore. That's okay. So we decide to order this encore. Now imagine a different scenario, and then after we do that, we move to the next one and try to order this. Now imagine a different scenario in which we don't have this. So we don't have this link. And this validator actually doesn't vote. This validator doesn't vote for the encore. So the encore in this case, f+1 is actually 2, so this one also does. So okay, this encore has only 1 vote. We need f+1, like I said before, so we need 2 in this example and only 1, so we cannot order it. But the tricky thing is that we don't have this node yet because we build it asynchronously. Maybe somebody else already have it, right? So in some other cases, I'm going to draw it in red. This is like your DAG, this is how you see it, right? And you actually see this, right? So you decide to order it and I decide to skip it, that's bad, right? That's what we want to avoid. So here's what we do. We rely on quorum intersection here because we need f+1 in order to directly commit the encore. And remember I told you that we build the DAG with 2f+1. We link every node links to 2f+1 from the previous round. Right? So and nobody can lie. It's also important property is that you cannot. We all see the same links. So if I directly committed, I mean you, right? You have these two things. If you directly committed this encore, it means that every future node here will have a path to this encore, right? This is like a simple quorum intersection. f+1 to f+1, we have at least 1 in the intersection. So we're going to leverage that. And let's say I don't see this, right? But what I do see is this encore, and I'm gonna order it because I have all this. This is my continuance of the DAG, so I do order it. So now it's very simple. All I need to do is to go back and see if there is a path between this encore to this encore. if there is a path, see here there is a path, that means that it could be the case that somebody, you in this example, actually directly committed this anchor. So I need to go and order this anchor before this anchor. This is how we maintain the safety. I also go now. If there is no path, the other logic. If there is no path, say this doesn't exist, then nobody could directly commit it. Again, this is just the opposite logic of the previous argument, just the other direction. So it's safe to skip it. Nobody directly committed it, so and we can prove it by induction. The reason it's safe to skip it because we're all gonna order this, and we're all gonna agree that there is no path because we all agree on the causal history, and then we're all gonna skip it. So that's basically it. That's basically the entire protocol. Very super simple, and from a system point of view, all you need to build is the DAG, which is actually not that simple. Nothing is simple when you build a distributed system.
The DAGs are actually very complicated.
Yeah, nothing is simple. We're doing it right now. A lot of corner cases and performance.
We were building this in 19. That's yeah.
Probably we are building hashgraph. What we were building?
Well, we had hashgraph. We were calling it transaction flow. It was very similar to this. There's a lot of caveats around,
yes,
like
there are.
when people withholding this or like retrieving it back. Like, do you, I mean, we can, let's go step by step.
Yep.
Yeah, so let's dive in. I guess my first question is, so for actually making ordering of this anchor, right, like you need to get to where you're starting to order this anchor.
Yes.
How long can it be that you kind of in this halfway state, right, where like the next anchor you cannot order yet because you haven't seen this, and so you kind of keep having this.
Yeah. Good point. Yeah, that's actually an issue with Bullshark, with like vanilla Bullshark protocol, because I mean, if the validators start crashing, you don't want them to become their nodes to become anchors, because then it's actually can go arbitrary. Also, if you think about the FLP impossibility result, the theory says that it can go indefinitely, but I mean, everybody are implementing partial synchronous protocols. That's kind of true for everybody. No matter what you do, there is a low bound if you have a deterministic protocol. There is a scenario, very unlikely, in which you don't have liveness, right? But so that's not an issue. But from practical point of view, if the validators start crashing, you can go far into the future of the DAG. So as Avery said before, we have this leader reputation that we use. So and this is already an improvement that we did in Shoal. So we added, one of the contribution there was to add a leader reputation to the DAG. So what we do is that once we order an anchor, we can look at the causal history and we can see, okay, these validators didn't participate, they didn't contribute nodes, there was a high likely that they are crashed or like very slow, they are struggling now, they are far behind. So let's exclude them from the possible sets of validators that can contribute anchors. So we end up with validators contributing anchors, and only the strongest validators will contribute anchors, and then it will reduce the scenario that we're describing, in which you will need to skip and go ahead in the DAG.
Got it.
So now to compare to leader-based protocols, what is like nice property of that is that in leader-based protocols, the leader can also be faulty, right? But there, it's unavoidable that you have to use these timeouts, right? So if the leader is faulty, typical timeout is around one and a half second, in which you just do nothing. You gave the leader a chance for 1.5 seconds just to realize that he actually crashed, nothing happened, and then you view change and continue. So this is like a 1.5 seconds penalty. The good thing about this is that you don't have this penalty, because the DAG you keep building, right? Network speed. And you might pay some latency price because you couldn't order this anchor, but this anchor is already here, you can continue. Whereas in leader base, you just do nothing for 1.5 seconds, and then you try again.
Yeah, no, of course, leaderless consensus has huge benefits. So what happens when, so let's say I have, let's say I'm this V4, yeah. So I sent out this with some confirmation, but I actually didn't publish this. So I didn't publish the round 2, but I sent out approval. So what happens to the...
You point to something that you didn't publish, right?
Yeah.
This is what you're saying?
Yeah.
So we will ignore you. We will process the node, but we will not add it to the DAG unless you give us this. We will fetch it from you, wait for you to give it to us, but if you don't, then we just not add it to the DAG, and we will wait to receive 2f+1 different nodes. And we consider this Byzantine behavior, and because there is only f Byzantine, 2f+1 are not Byzantine, so eventually we will get 2f+1 nodes that behave correctly. And then we can continue.
Yeah, so pretty much just like, I mean, obviously, so I'm sending this to some other validators. They haven't seen this, they'll go fetch it,
Yes.
right, from me. I'm, let's say, not maybe giving to some, not giving to others. Do they like rebroadcast like intermediate nodes to each other, or?
They don't. That's an implementation details. We
Yeah.
could, but we don't do it. What we actually do is that this. Well, I'm gonna give you. I point to a certificate.
Yeah.
And the certificate has 2f+1 signatures. So I can go and fetch from any of this. I don't need to fetch specifically for this. This is for load balancing. I can go and fetch for any of the signatures, any of the signing validators.
Wait, sorry, I didn't understand.
Yes, so like I said, a node here before, remember I said
where you collect the signatures.
I collect the signature, and then here I already send you something with the signature so you can add to the DAG. And when I point it back, I actually point it back to the certificate.
Like to the pretty much aggregated signature.
Yeah, the aggregated, but it has the bit vector, so I know who signed it.
Yeah.
So I could just go and fetch from this validator 4, but I don't want everybody to go and fetch from validator 4. So I'm gonna load balancing it. So I can use the information in the bit vector of the signature, because whoever in the signature
they have seen it.
Should have it, right? Should have the block, because they signed this. They signed it, right? So I will go and like load balance. I can fetch them. Yep.
Got it.
f+1 and the 2f+1 have it.
Yeah.
For sure.
Yeah, under the Byzantine assumption, at least f+1 are gonna have it. Yeah.
All right. And so you're progressing pretty much to next round after you have 2f+1
Yes.
published. So I guess like latency wise, like let's say I publish this and then I'm waiting to see everybody else's. Like meanwhile, I can be just ordering transactions so that I can. I'm just thinking what's the delay here looks like.
What's the delay?
Yeah.
So for an encore, to order an encore, you need this round and this round.
Yeah.
And to order this node, for example, is going to be ordered as part of this encode's causal history. So this is additional round.
Yeah.
And this one will actually require more. So because this will need this round, this node, this node, and this round. This will require 4. But in Shoal, we get rid of this. We can talk about this optimization as well. So in Shoal, we actually make sure that we have an encore in every round. This is one of our latest optimization. And the idea is actually very simple. It just took us some time to realize it. But let's say we believe that this protocol works, okay, safe and everything works. And like I told you, we have this, we divide it into 2 phases. First is to agree on the encores, and then we agree on everything. As part of agreeing on the encores, in particular, we agree what is the first encore we need to order, right? In this example, it was this, but not necessarily has to be, we might skip him and agree this, right? But if we believe Bullshark is correct, that's in particular also correct. We all agree which encore we need to order first. So in short, what we said, we just realized it, that it doesn't matter how we went in the future, what we did in the DAG, we can always deterministically go back and reinterpret the DAG again. So what we do is that, think about it, we start, like I said before, an instance of Bullshark. And we come into a conclusion that this is the first encore we need to order, right? Now, if we have to run the Bullshark protocol, the vanilla Bullshark protocol, we would skip this round and try to order this encore, right? And so on. However, we realized that we don't need to do it. So now we all agree this encore we need to order. We go order its causal history like before. And now we just decide, okay, let's kill this Bullshark instance. We don't care about it anymore. We can just deterministically agree, start over from this round and do exactly the same. We're gonna change the mapping and say, okay, this was the encore, now this is the encore, right? And now let's start a clean instance of Bullshark starting from here. And again and again and again, we'll continue with the same trick, and then we're having an encore in every round.
Mm-hmm.
Yes, and That's one. And then another one is the leader reputation, like I said before, because now once we order this encore, we can, not only that we are moving the encores, we can only change the mapping based on the history.
Yeah.
Yep.
So your assignment function pretty much changes based on the history.
Yep. And with this observation together, we can get rid of timeouts completely, because like I said before, this is a deterministic protocol. To fight FLP, we need to use timeouts. So one of the places we use timeouts in Bullshark is that we wait. Like I told you before that we build the DAG in network speed.
Yeah.
This wasn't entirely true. In order to get liveness, you need to wait for 2f+1,
Exactly,
but you also want to get a chance to get the encore. So you're going to wait for either, you wait for 2f+1
and the anchor.
And timeout or encore,
Yeah.
right? This is what you do. So now with this leader reputation, we actually don't need this, because if the encores are fast, like one of the fast validators, everybody gonna vote for them, good. If they crashed, if they crashed or slow, the leader reputation mechanism will make sure we just filter them out in the future rounds. So we end up with the strongest validator contributors encores, and we can just get rid of the timeouts. We just keep going. Of course, for the FLP, just to be, theoretically on the safe side, so nobody can argue we don't have liveness, right? So what we can do is completely unrealistic, but say like some configurable number of encores we cannot order, like we skip 10 encores, then we can say, okay, let's fall back to use timeouts. And then we go back to the same theoretical liveness guarantees we had before, where in practice we will never skip the 10 encores. This is like, you need a very powerful adversary to pull this off, right? So,
well, you pretty much need split network and somebody, manipulating DAGs on both sides.
Yeah, I personally really like it because I come from theory, and there, FLP, you take it very seriously, and you cannot do deterministic protocols without timeouts. So yes, we cannot, but we can like really corner it into some very, very theoretical place, right? So in practice, we will never use timeouts. So yeah, if you remember from the beginning, execution, then consensus, parallel execution.
Yeah.
So in parallel execution, the goal is really to execute the given transaction as fast as possible, and we can use all like threads in the system, right? And if we need a scalable algorithm to take use of the threads, and in order to be able to do it, the goal is to basically reduce conflicts. So that's the goal, reduce conflict. You want to execute in parallel, you need to reduce the conflict. So there are like a few ways to do it. One is like super trivial, which is like excess granularity. That's like meaning that if you group together some resources, resource group, and you group them together, and you have like resource 1, resource 2, resource 3, and this is like, you do it because it's friendly for your storage, you want to store them together, get them together, and then you have like one transaction that's trying to touch R1, and another transaction that try to touch R2. If the granularity of the access is an entire resource group, that's going to be a conflict, right? So you always need to try to make the accesses as low granularity as possible. So if I touch R1 and you touch R2, we should be able to go in parallel. So this is trivial stuff, I think. You just wanna. The more important thing you want to talk about is there is like this debate now about static versus dynamic parallelism. So I want to maybe touch about this a little bit. So we have static versus dynamic. Okay, and by static I mean that the user needs to specify the read and write set, like completely.
Yep.
And dynamic is completely agnostic. Agnostic. Yeah, meaning that the user doesn't need to give anything, just provide you the transactions. Well, this here, user needs to give you read and write set. So, yeah, so this is less convenient for sure. This is maybe a little bit inconvenient, but I wanna sets here. I wanna, from a performance point of view, I wanna touch upon it and why we decided to do dynamic. And I wanna go and maybe give an example of one use case, which is an order book. Let's say I want to implement a concurrent order book on chain. So for an order book, you have basically this price, and you have the, this is the amount. So, and say this is 10. So I wanna sell this amount and 10, this amount and 11, you know, and the higher the price, the more I wanna sell. And the buyer wants to buy a little bit and 9, more than 8, 7, like this is how order book looks. And then here we can have a match, right? This is what we do. So how would you represent something like this on chain? This is a market, let's say Bitcoin and Ethereum. So, so you have you need some sort of tree, concurrent tree. So you will have something like this. This is how you represent the sellers, and you will have also the representation of the buyers. Okay, now if you want to place an order, modify an order, cancel an order, you need to go to the tree and basically find your place and add an order, right? Or delete an order, move an order. So if you think about static parallelism, like Solana, Sui, these blockchains, you need to statically declare everything you're going to touch. Now the thing is that you don't know. You don't know which path you're going to go because you don't know the state of the tree. So there is nothing better you can do with static parallelism than to lock everything. You just lock everything, right? And if you lock everything, that basically there's no concurrency. If me and you are gonna place a bid,
we lock everything.
We lock everything. We're gonna go sequentially. Whereas in dynamic parallelism, say I want to add these and you want to add these. This is why it calls dynamic, because we dynamically on the fly realize what we're actually going to touch. So you're touching this area, I'm touching this area. There's no reason why we cannot go in parallel. So it gives you, like, dynamic parallelism gives you much more concurrency. We can place a lot of, and think of this big tree, right? So we can place a lot of bids concurrently, cancel, modify. Same on the other side. And this is like a strong argument why we choose dynamic, because this is one use case, but we believe like more complex use cases will come, in which static will just, the locking granularity is going to be bad, where dynamically you can just figure out a better complexity.
I mean, one of the limitations here is that also, like, you actually need to declare specific pieces of data that you're touching, which becomes a lot, especially in this case, and it expires quickly, right? By the time you prepared transaction, you sent it, and somebody already matched with this tree, right? And you're like, now your transaction is invalid. Now
a transaction aborts. That's the Solana, right? And they actually, no matter, you actually need to limit, right? Because you specify it.
Yeah, they have 16 pieces of account data that you can touch.
They can increase it, but somewhere they will need to put a limit, right? So if the tree is bigger, then you basically cannot. You need to hack some stuff in order to.
They have the crank for that.
Yeah, so dynamically, just no issue, right? You just go and figure out on the fly.
So how do you do that?
Yeah, good next question, yeah. All right, so let me erase this. So yeah, BlockSTM is like something we're really proud of. Actually, there are a few other blockchains that are currently already either implementing it or already deployed it, so it's which for us is like a big, researchers for us is a big deal. You know, somebody is using your tech.
Somebody's using your tech.
Yeah, this is more than any best paper for us, you know. So, so let's talk about BlockSTM. For BlockSTM, we're gonna take advantage of a few concepts. There is the STM, as the name concept, OCC concept, and multi-version data structure. Okay, so what is the STM? And all of these were like heavily studied in the literature. It just not so much in practice, unfortunately, but with this specific use case for blockchain, we figured out a very practical way to, and I will explain in a second what exactly led to this, to combine everything together into a system that actually performing very well. So STM stands for software transactional memory. Just think of like a layer of software that abstracts away all the concurrency you want to do. So it's like makes programming much easier. You don't need to deal with locks. You're just going to say, this piece of code I want to execute like atomically, send it to the library. The library will do the magic and it will execute it, which is perfect fit for blockchains, because what we have is actually transactions that we want to execute atomically. Now, this OCC is optimistic concurrency control. For STMs, we have two techniques. We have pessimistic concurrency control and optimistic concurrency control. And this most of the time gives better performance. And the general structure is that you want to go optimistic and you want to say, I want to execute the transaction. And you split into, you can execute a transaction and then you can validate the transaction. So you execute all the transactions and then you go after the fact and some later point and you validate. If validation succeeds, basically what you most of the time you are doing is that you are checking that whatever you read during execution, the values that they are still, they haven't changed. So whatever decision you make back then, they're still relevant, you can commit. So then you execute optimistically, then you validate. If validation passes, you can commit. Otherwise, you need to abort, retry, re-execute. So this is optimistic concurrency control, and multi-version data structure is just also like simple concept. Like say you have some memory location, and you have basically what you have is a mapping between the version and let's say you have like you have a list of transactions that you want to execute. So now instead of having one memory location for transaction, the transaction keep overwriting, you basically remember all the values that this transaction wanted to write to this memory location. So let's say 1 writes 100. Transaction 2 is going to write 200, and transaction 4 is going to write 400. So you have all this information. Why is it useful? Because for us, this is like, okay, why do we actually manage to make all these things work very efficiently? Is that we realize that we have this fixed order that we need to follow, right? Later we realize that we can like do whatever we want with the order, but eventually we just thought, okay, consensus gives us an order, we need to follow it, right? Yeah. And it has to be, not only the result has to be deterministic across other validators, it's actually need to respect the order. So it looks like a limitation. You limit your system, you probably should get like worse performance, but turns out that it actually gave us a better performance, and the reason is because we can follow the order. Explain it from a different point of view. So first, with this multi-version data structure, we can completely eliminate write-write conflicts. This is kind of known technique, nothing like we invented here, is that think about, these are the writes, everything is executed in parallel. Yeah. These are the writes, and now transaction 3 comes and want to read, right? So the way it works is that the transaction will traverse all the versions and will take the higher version that is smaller than the transaction number. So it will take this value. This is going to be the read. Because we're going to respect this order of execution. Transaction 3 needs to go after 2, so 3 is going to read the value that 2 wrote, right? So write-write conflict is not an issue. And yeah, remember the goal is to reduce conflicts. So no write-write conflicts. Now the question is read-write conflicts, right? How can we minimize the problem, minimize the number of aborts, the number of executions? So what we're going to do is actually also a simple idea. So let's, for example, in this example, say that transaction number 2, we executed it. We try to execute right optimistically, but then we figure out it needs to be aborted because
transaction 1 changed
conflict
something.
with some transaction 1, right? So what we are going to do is we're going to go back to this multi-version data structure. Now we can be much smarter. Remember I told you we have no idea at the beginning what are the read-write sets, right? But now we have much more information that we can use. Because we already know, we executed transaction 2 one time. We already have a good estimation where transaction 2 wants to write. Particularly, it writes to this memory location. So what we're going to do, we're going to delete this value, and we keep the entry, and instead we're going to have some button here. Okay, the button will represent the fact that there is high likely transaction 2 is going to write here. Currently, it's going to be re-executed, it's aborted, it's in the process of being re-executed, but it's high likely it's going to write here. So when transaction 3 now comes and read, it sees that there is an entry for transaction 2. The transaction should take this value, but this is the button here. Which means that there is no point for transaction 3 to go and execute, because it's going to be aborted, right? So instead, we're going to just suspend transaction 3, and transaction 3 is and we were gonna wake it up whenever 2 finishes, and then transaction 3 can go. So because we have this fixed order and we respect the order, we are able to reduce most of the aborts and most of the execution. There's really nothing better you can do if you think about it. Transaction 3 depends on transaction 2, right? So transaction 3 has to go after transaction 2. We couldn't execute them in parallel, and now we executed transaction 3 until as much as we could, but now we need to suspend, wait for 2, and then we can continue. This is like one of the core contribution of BlockSTM, why it can scale.
So you pretty much you run pretty much all of these VMs in parallel, and then when you see it reading something that like transaction 2 have updated, you just suspend it until
it's ready, until the value is ready, and then we can go again with transaction 3. Maybe in the future we will need to suspend it again, but we'll keep doing progress. Yeah. So another way we leverage this order is how we actually dispatch the tasks, right? We have this transaction, a lot of threads, which one is doing what, and the trick is always with SSTMs is to minimize the overhead. If you pay a lot of overhead in order to synchronize the thread, it's not going to scale, it's not going to work. So what we end up doing is that we maintain, like roughly speaking, we maintain 2 indexes, validation index and execution index. So execution is the next transaction, the index we're going to point to the next transaction we need to execute, and validation, the next transaction we need to validate. And because we respect the order, we also need to validate in order these things. So basically all the contention is going to be on these 2 indexes. When a thread wants to check the task, we're going to read both of them, see which one is the lower, and then going to perform a fetch and add, and then just go and take, okay, I need to go and execute this transaction, and then the pointer and then the index will point here. So the next thread will gonna come and take this transaction. So very, very minimum overhead for all this collaborative schedule for like the transactions, the execution.
But I guess there's a big RAM overhead of having this like transaction suspended, right? Not big, but like per transaction, there's some amount of RAM that you allocate for running VM and everything.
Yes.
And so as you kind of spinning up more and then going back to revalidate.
So yeah, that actually was an issue. The thing was that at the beginning, Move doesn't support, there was no async concept in Move, so we cannot just suspend inside Move itself.
Exactly, yeah.
We had to abort. The first version of BlockSTM, we had to abort the transaction and re-execute from scratch everything. And it was kind of annoying because algorithmically we didn't need to do it. We already reached some point, we can continue from there. So now what we are currently doing is that we are implementing our own thread garage, thread pool in Rust. Inside Rust, and we are going to use it. So we have all these abilities that we need to BlockSTM, suspend the thread, wake up the thread. So then it will give us another performance gain, I hope.
Got it. Okay, and then, so just from my understanding, so let's say you have 4 threads, you start executing all of this 4 in parallel. Let's say there is like all of them actually write, and then T2 reads from T1. So they'll write into some address, but then T2 actually specifically reads in T1. So they will all execute, T3, T4 will complete with their own, but T2 will suspend because it reads whatever T1 wrote out. It will then wait until T1 finishes, and then you'll like unsuspend it or restart it. You restart it, and then it will write out, but then actually that value will be replaced by T4, and you just kind of when you save the final state, you just take whatever the final values are for that
final step. That's exactly what's going to happen. And the cool thing about it is that if you don't have any conflict,
it's all in parallel.
You just execute, right? Nothing. You don't need to pre-execute. You don't need nothing. You just execute. But if you have conflicts, you already have pretty good estimation of what's going on, and for the future, you can be very efficient.
Okay.
Yep.
We kind of done most of it. All right, cool. Yeah, this is really cool. I think that this was really educational, hopefully. So thanks, Sasha and Avery, for joining. And join more episodes of Whiteboard Series. Thank you.